Hello and welcome back to Rotary Rocketry. So just a quick update on our YouTube channel name. We recently changed the channel name to Rotary Rockets, but unfortunately when we went to apply for our YouTube handle, our Gmail account, and our website domain name, Rotary Rockets was already taken on all of those services. So we just recently changed the name to Rotary Rocketry so that we can have the same name across all our services. Now, we do have a website domain name, but that does not mean we have a website yet. We just reserved the domain name, so in case we want to have a website later, we'll be able to have the same name for that as well. Now, on to today's video. Welcome to Rotary Rocketry. Today, we will be testing both a new rocket and a new motor. This is a continuation of our previous video where we were developing a new PVC motor. We're trying to develop a motor that's simple, easy, inexpensive. Now this isn't the exact motor that we were trying to develop. We were originally trying to develop a motor with a PVC casing and a completely reusable nozzle. If you want to go and take a look at that video, there's a link down in the description. There'll also be a link on the screen at the end of this video. So this is what we ended up with. The last test of this was successful with a ground test, had a good amount of thrust. The intention was to build a PVC motor that was powerful enough to launch our 4-inch style of rockets. This is an 1.25 inch PVC casing and it has 6.5 inches of sugar fuel inside. Now I do have some ideas in the future to actually improve this design. This is still a prototype. The newer design would hopefully be a little less expensive to build. It'll have one less fitting. And also I'm thinking about increasing the diameter of the piping just a little bit to get a little bit more power. But we'll see about making those changes depending on how today's launch goes. Now for today's launch, we do have a brand new rocket. This is our Eliminator Nano. Now, if you've been following our channel, you'll see that it looks pretty much like a lot of the other Eliminator series rockets that we've been flying. 4-inch diameter body tube is pretty standard. However, it's a little bit shorter, and that's where it gets the Nano name. We've also changed this one to a 3-fin style. That's going to decrease the weight as well as decrease the drag and hopefully help us with the performance of the launch with this smaller motor. Now the reason this video has taken a little longer to get out than some others is I've done a lot of redesigning on this rocket. Now from the outside, yeah, it just looks like our standard Eliminator rockets that we've already built 4 or 5 of them that look exactly like this. However, it's the inside that has had major updates. This fin system, the installation for this is our easiest fin installation system yet. You simply snap the fins into place, put in the adhesive, slide in the retaining ring on the bottom and the top, and it's done. It literally just takes a few minutes. And then up at the top, we have our nose cone that we are calling the Apogee nose cone system. Now there is no electronics bay in this rocket. The electronics bay is in the nose cone. It's a combination nose cone and electronics bay. So let's take a quick look at some of the features that we've got here. The Apogee nose cone is our own invention. We've got several different shapes and sizes of nose cone that are compatible with this. The nose cone simply screws off. Inside, we've got the flight computer. We're going to be using the Egg Timer Apogee flight computer. This has a custom slot where the flight computer simply slides into place, requiring no fasteners. Same with the battery, slides into its holder. And then on the bottom here, there is our ejection charge, and it has a cap here that threads out so you can replace that ejection charge really easy. And the whole thing attaches to our recovery line. So you simply activate the flight computer, thread on your nose cone, drop it in the rocket, and you're ready to go. Now this will be the first launch test of the 4-inch version of our Apogee nose cone. In our 1,000 subscriber special, we launched a 3-inch version of this. Unfortunately, the bottom section was damaged when the parachute deployed. It just kind of ripped it apart. I've done a lot of updating to reinforce the bottom and make it much stronger, so hopefully this one will hold up. So we're going to go ahead and get out to the launch site and launch this. All right, we're setting up to launch. I just wanted to get it on video just to clarify. This is the number 20 nozzle that we're testing today in this. On our testing, the 18 exploded and the 22 had a hard time building up pressure. So the 20 seemed to work good, and that's what we'll be launching today. Oh! Oh boy. Okay, so there's a lot to talk about that launch. So much that I actually had to make a list of the good things and the bad things so that I wouldn't forget anything. So let's start with what went good with that launch. First off, the motor did not explode, so that's good. Now, we didn't expect this to explode because we did ground test it, but we only did one ground test and you never really know. It's nice to see a second test of this motor and have it successful, so pretty confident about that number 20 nozzle size. Now, unfortunately, we're probably going to change the shape and size of the fuel in here to a larger amount of fuel, so we'll have to re-ground test when we do that and may even end up changing the nozzle size. But for now, that motor did not explode, so that's good. Second thing that went good, the rocket did launch. Now, there's more to talk about on the bad section here about that launch, and we'll get to that, but it did fly up into the sky, and that's what the rocket was supposed to do. So I guess we have to say that's a good thing. Number 3, the rocket held together. This was a test of the motor primarily, but we were also testing a new fin installation system, as I mentioned earlier. So it was good to see that the fins didn't get ripped off, because that was really what was the danger of that new mounting system. Now, obviously we damaged a fin, but that's in the landing, so we're not going to count that yet. So the new installation system for the fins seems to be a success. Last thing that went good, the flight computer. As expected, the egg timer apogee, it did detect the apogee, it fired the ejection charge, out came the nose cone and kind of the parachute. We'll get to that in a minute, but the flight computer performed the way it was supposed to perform. I guess also on the good side is we did reach 1,206 feet in altitude, which is just about the range I was shooting for. Our other all-metal motor with our Eliminator rockets, which are this size but a little bit taller, we get about 1,400 to 1,500 feet with that, and we were shooting for somewhere in that range with this, even though the motor is a little bit smaller. So 1,200 feet is definitely where we were interested in getting with this rocket and this motor. So that's all good. However, on to the bad stuff, which I'm sure you noticed some of that if you've ever seen a rocket launch before. So the first thing I've got here is very slow takeoff. So I'm going to show you a little loop of video here of the rocket on the rod and just coming off of that 8-foot rod. And I'll zoom in a little bit and you'll see this looks like it's in slow motion, but this is not. This is the actual speed of the video and the rocket coming off of the rod. It is clearly way too slow. We are just not building up enough pressure and enough thrust in that motor fast enough. Now, there's some differences in how the fuel is poured and how the base cores are set into the rocket. And I do know the difference between a positive burning core, a negative burning core, and a neutral core. And we're not going to go into the mathematics of that, but just for simplicity, we poured this the most easiest way we could, and it ends up to actually be a positive burning fuel core, which is not necessarily the most efficient fuel core, but we did it for simplicity. It was the easiest to make. So on a positive burning fuel core, just in a perfect world as an example, if it starts burning at 0 pounds of thrust, when it actually starts to consume the fuel, the thrust goes up in an even line like that until the fuel is done, and then no more thrust. It's not the most efficient way because when you're trying to get the rocket off of the launch pad, which is kind of the most critical point to have sufficient amount of thrust, that is the moment in time where you actually have the least amount of thrust. And that's pretty clear in that video. Our friend that was there at the launch said afterwards it looked like the rocket lifted up, and just as it got off the rod, it looked like a turbo kicked in and it just took off. Unfortunately, it was already off of the rod by the time most of the thrust kicked in, and that's why you see the rocket kick off to the side, because the motor is literally trying to push the rocket out of the way. I measured it as best I could on the screen. It looks like the rocket tipped off to about a 20-degree angle. So clearly we're not building enough thrust fast enough in that motor. Number 2 on the bad list, parachute got caught in the recovery cord. So here's a close-up shot of the parachute afterwards, clearly wrapped up and bound up in the recovery cord. It was so tight and the wind was so perfect that if you pulled on both sides of that, it literally just got tighter around the parachute. There was absolutely no chance for that parachute to deploy. Now that is really, really weird. I thought about that for a long time after the launch. With this parachute, it simply had the shroud lines wrapped around the parachute just one time, just to keep it nicely bound up, and then everything else was shoved in, but everything else was shoved in on top of it. And I don't know if it was G-force or just the parachute being pulled up through the recovery cord. Somehow it just got in there, and then as soon as the tension was on the whole system, it was just completely caught up and it was never going to come out. So that was just terribly unfortunate. I think I'm going to wrap up the recovery cord a little bit differently in the future, so hopefully that doesn't happen, but that was just a terrible, unfortunate thing. Number 3 on the bad list, rocket and nose cone damaged by hard landing. Unfortunately, we didn't get a very good video shot of the rocket actually smacking the ground. Both cameras were a little bit far away to catch that. But clearly you can see one fin is no longer quite as straight as the others. I think I can actually fix that fin. I'm gonna try to fix this rocket. If I can't, we'll just end up building an identical one to it, but it's not the worst thing in the world. The nose cone, the top of it seems to have hit the ground. You can see the dirt mark here, so it just kind of smacked the ground, knocked the tip off. So we'll just have to make a new one of those. There's a way to reinforce that we learned recently with the 3D printing method, and I think for the tips of these nose cones I might do that reinforcing method just for maybe the last inch or so, just so the tips aren't quite as weak. Unfortunately, I can't say that this nose cone system was a complete success because there were 2 things that did go wrong with it. So down on the bottom here we have the ejection charge that sits in this little holder here. This holder had a little lip that came around the top of this ejection charge to hold it in place, so that as the rocket is going up, the ejection charge doesn't just slide out of the holder. That entire top ring piece that goes around there is completely gone. It just got sheared off and fell out of the sky somewhere. That was very unexpected. Not entirely sure why that happened. Now 3D printing, because it's printed in layers, the weakest part is going to be a shear across a layer. It just looks like it sheared out a layer and just popped that off. There are some reinforcing techniques we can try on that, as well as making that a little bit thicker. But that was really completely unexpected, so I'm not exactly sure what I'm going to do about that, but we will think about that one a little bit more. The other thing that was damaged on this, with the vent hole that allows the air to breathe between the air chamber of the rocket and the air chamber for the flight computer up here, we had a little filter, a little fabric filter that was sitting in this hole here, and it was just held in with some silicone adhesive. That was really just to keep gases and particles from the ejection charge from getting up to the flight computer area. Now, I think it kind of did its job, but at the same time, it completely blew that fabric piece out. There's some blackening around that, like it might have gotten some char from just the hot gases. Now, I didn't actually use a piece of fabric for that. I used a piece of batting, which is just like a thin pad. Just because when you breathe through batting, it breathes very well. It's not restrictive. And I didn't want any air restriction between the two chambers. But it's not very strong. If you poke it with your finger, you can poke right through it. So I think that's maybe a better choice for fabric there. Something that breathes good but is still strong would be a better choice there. But we do like having that filter there. Now, possibly I'll re-engineer that to be able to replace that filter easy as well. I don't mind replacing that fabric filter every time we launch, but in this technique here, it's glued in with adhesive, so it's not really easy to replace. But if I had to do a replaceable method there, I could do that as well. But we'll use a stronger fabric for that next time. So, we need to decide where we're going from here, because there will be a part 3 of this series. So as I said before, I'm thinking about making changes to the motor first of all. And we're using 1.25" PVC here. I think I'm going to go up to 1.5" PVC. Now that's not going to increase anything with our initial thrust, because it's only the center core that's burning. In conjunction with the increase on the diameter here, I'm also going to increase the core size. This is cored with a 3/8 rod. We'll core the other one with a 1/2 inch rod. So if you calculate the amount of increase there of the amount of fuel that's burning as soon as it ignites the center core, the difference between the 3/8 core and the 1/2 inch core is going to be about a 38% increase. So that very initial immediate thrust when the motor just gets starting to go and burning that whole center, we should get about 38% more thrust. But that's assuming that we can stay with the number 20 nozzle with that bigger size amount of fuel. If we have to increase the nozzle size, then the thrust is going to drop back down. So that's going to be something we're going to have to test and see how that performs. Otherwise, there might be some changes we need to make to how we're pouring this fuel core so that we can get more surfaces burning. Again, this is poured for simplicity, so rather than efficiency, the only thing that's burning in here when this first ignites is the center core and the top surface. In a perfect world, you'd prefer to have at least the top surface and the bottom surface, or maybe even a center split where you have 4 end surfaces burning along with the core in the middle. Then you would get a fantastic liftoff, which is exactly what our metal motors do right now. But unfortunately, there's problems when you try to do that in PVC. So that's why we're trying to just do it with a single core. But that's creating some thrust issues. We're going to play with that. I'm going to try and fix this rocket, as I said before. Hopefully that'll go fine. Worst case, I just have to build a new one. It's not a big deal. With that new fin installation system, it literally just takes a few minutes. And we'll be back. So I hope you enjoyed this video. Maybe you found it interesting. The launch was definitely interesting. We'd really appreciate you clicking that subscribe button if you're not already subscribed, the like button as well. It really helps our channel out. And we'll see you next time on Rotary Rocketry.
Whew.